Okay, let's look now at complex number division, or dividing one complex number by another. So if we take a plus bi divided by c plus di, the trick to use here is kind of the same one we used when we were rationalizing denominators. You just multiply the top and bottom of this fraction by the conjugate of the denominator. The conjugate of a complex number is the number with the same real part but the opposite imaginary part. So in here, if I have c plus di in the denominator, I multiply the denominator by c minus di, and of course then I have to multiply the numerator by the same amount. We're going to use the basic pattern that x plus y times x minus y is x squared minus y squared. So here we get c squared minus di, quantity squared. That's the sort of the f and the l from FOIL, and the o and the I cancel each other out. cdi and minus cdi, so they're going to cancel. When you square di, you're going to get d squared I squared, but I squared is -1, so it changes that subtraction to an addition. And so we're going to end up getting c squared plus d squared, in other words, the square of the size of the vector of the complex number c plus di. Now, of course, in the top, you're going to use FOIL and multiply this out. A times c is ac. There's your f. Your o is minus adi. The inner product is bci. And then the last times last is minus bd I squared. Of course, I squared is -1, so this becomes plus bd. Okay, and then we can combine like terms here. So ac plus bd over this c squared plus d squared is the real part, plus, now put the i's together, you get bc minus ad times I. And then we got this in the denominator, so it's bc minus ad over c squared plus d squared I. And so there is that's what the answer is. The quotient is in that with those general forms. So again, the basic concept is you just want to find the conjugate of the denominator and multiply the numerator and denominator by that. Then just use things like FOIL and so forth and distributive property, and remember that I squared is -1. Now, it turns out that there's a really nice way, just like there was a nice way to multiply two complex numbers, there's a really nice way to actually add them, to divide them as well. And it does what it looks like you should do here in this form. You take if R and S are the positive numbers that are the absolute values, and then we have angles alpha and beta, we're just dividing R divided by S to get the magnitude of the quotient, and we're subtracting the angles to get the angle of the quotient. So it's because these angles operate like exponents when multiplying and dividing that we use the exponent kind of notation. So that's called the polar notation. Now, let's actually prove that this last result is true. And this is going to be very similar to our proof of the last thing that we did with multiplication. So, again, let's let z be the complex number a plus bi, w is c plus di. So a, b, c, and d are real numbers, w and z are complex numbers. Alpha, beta, and theta are going to be angles. Alpha is the modulus of z, beta is the modulus of w, and theta is the modulus of z divided by w. Now, the first thing we want to do is look at the absolute value of z over w. We want to show that that's the absolute value of z divided by the absolute value of w. And that will prove that the coefficient here is r over s, like this, like it should be. Okay, so now remember, z over w, we worked out the details up here. So this is, you could take this as actually the definition. So it's ac plus bd over c squared plus d squared plus bc minus ad over c squared plus d squared I. So there's the quotient. And we're going to find its norm or absolute value. So we square each part, the real part and the imaginary part, add them up and square root. So we square this, the denominator, I'm just going to leave it as c squared plus d squared squared, which it is in both cases. And the numerator, we're going to square this out. You square the first term, square the last, multiply and double it for the middle. So here we square, we get a squared c squared. Square the last is b squared d squared, and multiply and double it for the middle gives you 2a, b, c, and d. Similarly over here we get a b squared c squared, which I wrote last, positive a squared d squared, which is first. In the middle we multiply and double it, we get negative 2abcd. These have a common denominator of c squared plus d squared, so we just add everything together in the numerator. And notice this plus 2abcd and this minus 2abcd cancel each other out. And so we're left with this. It turns out that this numerator is exactly a squared plus b squared times c squared plus d squared. So we get the square root of the top over the square root of the bottom. The square root of c squared plus d squared squared, the square and the square root cancel. You get the absolute value of c squared plus d squared, but which is just c squared plus d squared. Those are even powers, that's a positive number. Now in the numerator, let's check out that I've said this factors this way. We can check it with FOIL. A squared times c squared is the first term, there's your f. Your O is a squared d squared, that's the third term. The inner product is b squared c squared, that's the last term. And last times last is b squared d squared, which is the second term. And we see that so that it does actually factor that way. Of course, this is the square root of a product is the product of the square roots. These are all real numbers here, so we know that works. So we get the square root here and here. The bottom we could think of as the square root of this squared. And then if you notice, then the square root, these two square roots right here on the second part cancel each other out. And so we get square root of a squared plus b squared over square root of c squared plus d squared. But the square root of a squared plus b squared is just the absolute value of a plus bi, and the square root of c squared plus d squared is the absolute value of c plus di. Well, that's the absolute value of z over absolute value of w. So we show that the size of the complex number, the magnitude, the norm or absolute value, whichever word we use, of z over w is the absolute value of z over the absolute value of w. Okay, now let's look at the angle. Now remember, alpha is the angle for z, and beta is the angle for w. So cosine of alpha is the real part of alpha over the real part of z over the norm of z. So it's a over z, a over z, right? The cosine of beta is the real part of w over the norm of w. So that's c over norm w. Plus sine of alpha. Sine of alpha is the imaginary part of z over norm of z. So that's b over norm z. And the sine of beta is the imaginary part of w, which is d, over the norm of w. So both cases, these have a denominator of norm of z times norm of w, and this first one has AC for the numerator. This one has BD. We can get they have a common denominator, so we just keep that and add the numerators. So we get AC plus BD over norm of z norm of w. And now I'm going to write that out. Norm of z norm of w now is square root of a squared plus b squared, and then times the square root of c squared plus d squared. And what I'm going to do with this is I'm going to take this fraction and multiply by 1 over c squared plus d squared. Remember, c squared plus d squared is the square root of c squared plus d squared squared. So in the top, I get ac plus bd over c squared plus d squared. And in the bottom, I'm going to get, one of these cancels, I get square root of a squared plus b squared over square root of d squared plus c squared plus d squared there. The denominator, if you look, that's exactly what we had right here for the norm of the quotient. And if you look right here, AC plus BD over the square of C plus square of D, that's exactly the real part of this quotient. So what we have is the real part of the quotient Z, where are we? The real part of the quotient z over w divided by the norm of z over w, and that's exactly the cosine of that angle theta. Now, similarly, we work with sine of alpha minus beta. Sine alpha minus beta is sine alpha cosine beta minus cosine alpha sine beta. Sine alpha, once again, is b over norm of z, cosine beta is c over norm of w, minus cosine alpha is a over norm z, and sine of beta is d over norm of w. Once again, you got a common denominator of norm of z norm of w, and here, so in the top, you're going to get BC minus AD. Okay? Again, we're going to write the norm of ZW. Actually, I really don't, this is true, but I don't really need this step. Just leave it like that. That's BC minus AD over square root of a squared plus b squared times square root of c squared plus d squared. And just like the last time, we're going to multiply top and bottom by 1 over c squared plus d squared. In the bottom, I'm going to think of that c squared plus d squared as square root of c squared plus d squared, and then multiply by that twice. So in the top, I get bc minus ad over c squared plus d squared. In the bottom, one of these square roots cancels, but you got the other one, so you get a squared plus b squared over c squared plus d squared. So just like last time, that denominator is the norm of z over norm of w. But this time, bc minus ad, that's the numerator here, and then you had c squared over d squared. That's the imaginary part of the quotient. So that's the imaginary part of the quotient over the norm of the quotient. Well, that's exactly the sine of the angle. So we showed that the sine of alpha minus beta is the same as the sine of theta. The cosine of alpha minus beta is the same as the cosine of theta. And that's enough to make the two angles the same, or at least coterminal. So theta could be alpha minus beta. And so that means the modulus of z divided by w is the modulus of z minus the modulus of w. And so we are justified then in sort of writing it in this polar form and use our normal rules of exponents. We just divide the coefficients and subtract the exponents. And so it works out nicely that way, which is why we use that notation, because it's very convenient. Now, when we look over here at our example, we have -1, -3 for z, the blue dot here, and the green dot is this dot right here at w, -2, 1. So it's -2 plus 1i, and this one is -1 minus 3i. And what about the quotient? Z divided by w is this black dot here, and so we get well, it turns out to be -1/5 plus 7/5 I. And that looks reasonable there. Okay, so it goes about 1.4 in the y direction, which seems about where it is. It goes about -0.2 this way. Yeah, that's good. That means its distance from the origin, length of that dotted line, is about 1.414. Okay. And the angle is about -4.57049 radians. Now, that is measuring it in a negative direction, so it's going this way. It's not the only way to get it. You could, of course, add, anytime you have it in the form r e to the I theta, you can always add multiples of 2 pi to theta and get another possible angle that works out just fine. So that covers complex division. So by now we've talked about how to add, subtract, multiply, and divide complex numbers.